So now, as Santa Claus says in Elf, we've had another very successful exam, so now it's time to start preparing for the next exam, right? Yay. Right, so we've been talking about how we know what we know about organic molecules. And one thing that we discussed last time was just the use of infrared spectroscopy and mass spectrometry to, let's see, where is my stuff? Where am I going? Was that, what day was this? Oh, the screen's not even on. Good. I'm trying to find the last, oh well, sorry. What a day. We were talking about infrared spectroscopy and IR and mass spectros. I'm going to get that wrong, man. Now I've got a complex about it because I told you it was a big deal. Right. Mass spectrometry and infrared spectroscopy. We use IR to identify functional groups, particularly alcohols and carbonyl groups. It's useful for more stuff than that, but probably not within your immediate future. We also talked about mass spectrometry, which is basically how we get... Sorry, what? Still not up? Okay. Did I miss something? Somebody started talking at me. Am I hearing voices? That's kind of concerning, isn't it? All right. Yeah, I hear it too. By the way, excellent cameos in today's episode of The Mandalorian. Yeah, you wake up early for this kind of thing, yeah. All right, anyway, we were talking about mass spec and being able to identify the mass of to make sure you've got the correct molecule present. There's a few things that are going to be useful to you about mass spec. The first is just if you have the molecular formula for a molecule, how do you come up with a hypothesis as to what its structure might be? And there's kind of a cute little trick, as I tried to show you last time. Every double bond or ring that you form removes 2 hydrogens relative to the fully saturated hydrocarbon. So you learned that the fully saturated hydrocarbon has a formula 2n plus 2 for the number of hydrogens, where n is the number of carbons. But then I showed you how for the introduction of 1 double bond, you basically lose 2 hydrogens. This is true for a ring as well. If you have, let's see, C4H10, right? Butane versus C4H8 cyclobutane. Again, you are losing 2 hydrogens. Basically, because if you're thinking about a molecular model set, in order to close the ring, you have to pop off 2 hydrogens on the end so you can connect the 2 carbons. So every double bond or ring leads to 2 hydrogens missing from what you would expect for the standard hydrocarbon. All right? Why do you care about that? Well, I don't know. But if you have a molecular formula like this, it turns out this formula alone is probably all you need to solve the structure of your molecule. Because if I calculate the number of hydrogen atoms expected for the saturated hydrocarbon, that would be 14. Instead, I actually have 8, but actually that means 6. So that means I have 8 hydrogens missing relative to the saturated hydrocarbon, which translates into, if I divide by 2, because there's 2 hydrogens per pi bond or ring, I have 4 pi bonds or rings in this organic molecule. And the only way you can actually arrange a molecule with 6 carbons to have 4 pi bonds or rings in it is benzene. So right away, this method of comparing hydrogens to what you might expect for a saturated hydrocarbon versus what you actually have can narrow the number of structures you are considering as possibilities. Okay? So this thing of, how many pi bonds or rings do we have in your text, and I believe in chapter 10 this was called degrees of unsaturation. I sometimes call it double bond equivalence. I've told you my air quote story, haven't I? No? Okay. Well, air quotes are, I guess they're not air quotes when they're on paper, but it's an entirely overused thing, and sometimes some of my relatives have not used them appropriately. For example, when I was engaged to Amber, my aunt threw her bridal shower and said, "Come to the bridal shower of Josh Price's fiancée, Amber." She didn't mean it that way, but if that is even her name. And then, this is really great. I told you my wife's in a PhD program in School of Family Life right now, she just finished the prospectus for her dissertation, so she's maybe a few months out from finishing. Her aunt sent her a happy birthday card that said that happy birthday, and I'm impressed, and hope you are successful in your education. So anyway, unintended irony, I think, but we're saving that one. We're framing it. It's kind of funny. All right. So I'm sorry. Double bond equivalence is sometimes what I call it. Of course, organic molecules often have more things in them besides hydrogens and carbons, and you need to know how to adjust the number of hydrogens you expect based on the presence of heteroatoms. So take a look at this. Let's make it simple. C2H6 is just ethane. I could add ethane to ethanol. Notice that the addition of that oxygen doesn't change the number of hydrogens in the molecule. And that's because oxygen has to be bonded to two things. So it's easy to insert an oxygen into a molecule without changing the number of pi bonds or rings. You just insert the oxygen in between one of the carbons and hydrogens. So what that means is the inclusion of oxygen in an organic molecule will not change the expected number of protons for a saturated hydrocarbon. So the impact of oxygen on number of expected protons, none, no effect.
What about ketones?
Well, then you've got a double bond, right? So what I'm saying is, in calculating the number of hydrocarbons and number of protons you expect for a saturated hydrocarbon, you don't need to adjust your estimate for oxygen. So to address your question, what about a ketone? This would be C3H, H6O. So what I'm saying is, to calculate the expected number of protons for the saturated hydrocarbon, you're still going to do 2 times the number of carbons plus 2, which would be 8. You still observe 6. That means 2 divided by 2 equals 1 pi bond. So there's no need for an adjustment for oxygen. Now that may appear like no big deal, but let's look at what happens if you don't make an adjustment and you incorporate a halide. Okay? So in incorporating a halide, because a halide's only bonded to one thing, we really do replace one hydrogen with a halide. Now, if we made no adjustment in our calculation of what we expect, 2C plus 2 equals, sorry, not 8, I'm really struggling with the math, 6. How many do I actually have? 5. 1 divided by 2. What the heck does half a double bond equivalent or half a degree of unsaturation mean? Nothing. Doesn't mean anything. It means that you needed to adjust your expectation. I feel like there's a life lesson in that, right? A lot of times we should adjust our expectations. So what do you do for the presence of a halide? Well, we're going to modify our expectations so that we know that each halide actually replaces a hydrogen without introducing a double bond. So we're going to actually subtract the number of, X is going to be for, in general, halogens, chlorine, fluorine, bromine, iodide, to adjust how much we expect for the saturated hydrocarbon. In this case, that's 2 times 2 plus 2 minus 1, 5. We actually have 5. Now the math works out. We have 0 degrees of unsaturation. Okay? Does that sort of make sense? So you can ignore oxygen, and actually the rules apply for anything in the column with oxygen. So if your molecule contains sulfur, also in calculating the number of hydrogens you expect to have, sulfur has no effect. The same would be true for the stuff below sulfur, but I can't think of molecules right now. I can think of one molecule with selenium in it, but or maybe 2. Other than that, no. So that'll be enough for us. So the effect of a halide is subtract 1 in your adjusting your expectations. Now let's look at the effect of adding a nitrogen. C2H7N. Each nitrogen that you introduce in the place of a hydrogen, because nitrogen can be bonded to 3 things, you put a nitrogen in place of a hydrogen, you got to add that hydrogen on plus another to have a neutral molecule. And I guess I should say overall, these rules are for neutral molecules. Let's again see what would happen if we calculated our expectations without any adjustment here. That would be 2 times 2 plus 2, we would expect, minus the number of halides, which is 0, we would expect 6 hydrogens. We actually have 7. Negative 1 divided by 2. What is minus half a double bond or a pi bond or a degree of unsaturation? Doesn't make sense. That's a clue that we need to adjust our expectations. So what we're going to do is we're going to expect 1 additional hydrogen for every nitrogen in a molecule, provided that there are no pi bonds or rings. So if we do this now, that's 2 times 2 plus 2. There are no halides, but there's 1 nitrogen equals 7. Minus 7 is 0 degrees unsaturation. All right? Why do we care about that? Well, you can just memorize the formula. The degrees of unsaturation equal 2 times the number of carbon plus 2, adjusted for halide and nitrogen, subtracted by the number of hydrogens you actually have, and then divided by 2. This is the number you expect. And that will tell you how many pi bonds or rings or the molecule has. And as I said, this can help rule out a lot of other possibilities when trying to solve the structure of an organic molecule. Why does this matter? Because, well, that's an excellent question. I will tell you. Thank you for asking. We will get to the point where I'm going to, no, it's not a, yeah, that's too bad. We're going to get to a point where you're going to get a spectrum like this. You're going to be given molecular formula, an IR peak. What functional group could this be? I know you don't know because you haven't been paying attention to IR. CO double bond, right? Okay. That'll be something you'll want to know by the time exam time comes around. Then you can do the number of pi bonds or rings present in this organic molecule. 2 times 4 plus 2, ignore the number of hydrogens, number of carbons, subtract the number of hydrogens that we have, and divide by 2. That means we have 1 double bond equivalent, or 1 degree of unsaturation. That tells us we have 1 pi bond or ring. And actually, we've already accounted for that pi bond in the presence of the carbonyl group. So we can use this information to corroborate multiple lines of evidence, and then you can start to generate structural hypotheses. Now, what the heck is all of this? You didn't want to know, but I'm going to tell you. And that's where we get into something that's called nuclear magnetic resonance. Before we move on, any questions about degrees of unsaturation? Yeah?
Will you ever give us a problem where it's like calculating the number of pi bonds versus number of rings based on like
Yeah, it's a good question. Can you tell based on this calculation whether the degree of unsaturation comes from a pi bond or a ring, not without additional data? Sounded like Palpatine, not from a Jedi. There is an experiment you could do to tell. If you think about these two molecules, the alkene and let's actually just draw this, the alkene isomer with the same molecular formula, C4H8. They both have 1 double bond equivalent. If you do catalytic hydrogenation, you can convert this into C4H10, but catalytic hydrogenation on the ring compound would have no effect. And so that's one way to tell. If you watch how the molecular formula changes after that reaction, you can tell. Okay, others? Right. So, nuclear magnetic resonance. Thanks to the President of the United States when you guys were like little people, George W. Bush, we can now pronounce nuclear as nuclear. I think that's a legitimate dialectical pronunciation now. So nuclear, I can't do it with a straight face. Nuclear magnetic resonance spectroscopy. So spectroscopy tells you you're going to be shooting some form of EM, electromagnetic radiation, at a sample and seeing what is observed. Now, there's a lot of physics in the background for nuclear magnetic resonance. Fortunately, you don't have to be a physicist to use it usefully. It's just like your phone. You don't need to know all the ins and outs of the electronics in order to be able to use your phone properly, though if it has issues, it helps to know so you can fix the thing. In our department, we have 2 or 3 nuclear magnetic resonance spectrometers, instruments that do the spectroscopy. They're in the basement, and they're managed by Professor Scott Burt, who has an extensive background in both the theory and the practice of these instruments. And we'll talk about how they work. Yeah?
They're like stupid expensive and very fragile.
Stupid, expensive, and very fragile. Yes, you're looking at probably close to $1 million, depending on how powerful the instrument is, and it can be more than that. And they are pretty easy to break. And so there are lots of protocols in place to protect the instruments from humans. Yeah, we can talk more about that. I want to give you just a bit of background on the physics. So, like electrons, protons and neutrons have a quality called spin. It's an angular momentum property. It doesn't mean that the proton is actually spinning around, because it's not, but it has a property that you would expect for a macroscopic particle if it were charged and it were spinning. You know from physics that charged particles that move in a circular path generate a magnetic field, And so you can think of certain nuclei as being little magnets. And there's actually, unlike you're used to thinking of with sort of the Earth's magnetic field, there's a north pole and there's a south pole, there's two different spin states. There are multiple combinations of spin angular momentum for various nuclei, multiple spin states possible. That gets into the weeds in the physics that we don't really want to know about. The simplest nuclei to work with are those that have spin 1/2. And that just means there are two spin states possible for these nuclei, sort of a north pole and a south pole. And among the nuclei that have spin 1/2 and whose physics are fairly easy to interpret are the major isotope of hydrogen, proton, okay, and a minor isotope of carbon, or C13. Just to point out, I'm going to get this wrong actually, so let's see if I've got it anywhere. The natural abundance of C13, what is the natural abundance of C13? Hey, how about that? 1%. Whereas, let's see, what is the natural abundance of hydrogen? 99. Okay. Nice. Okay, so that means that nearly all of the protons in organic molecules you can see and think of as magnets. And then 1 out of every 100 carbons in an organic molecule will be C13 and will function as a magnet. And of course, when you're dealing with moles of molecules, 1 out of 100 is still really, really good odds. You still likely have enough molecules or enough atoms of C13 in a sample to make an observation. Okay, so what I'm going to describe here is an overly simplistic view of the physics, but that's because I only understand it at a superficial level. If you want to know more, Dr. Burt would be so thrilled to sit down with you and talk about it. Right. So when a nucleus has spin 1/2, there are two different states it can adopt in the presence of an external magnetic field. So we're going to define our external magnetic field as B, and everybody puts a 0 on it, and so I'm not going to call it B naught because I think that sounds like be not afraid or something like that, which is a great message, but we'll just call it the external magnetic field, sometimes represented by this kind of arrow, which again is confusing because we've used that as a retrosynthetic arrow, so I didn't make this stuff up. Let's just, that's a little, I don't know, different. So in the presence of an external magnetic field, which is a vector quantity, there are two possible spin states that a nucleus like hydrogen or carbon 13 can adopt. One is, we'll use the term, just for our purposes, it's not anything to memorize. We'll use the spin state, we'll call it M for a particular nucleus. One is the spin 1/2 state, where the little magnet of the nucleus is aligned with the magnetic field. And then the other that is allowed by the physics and the quantum mechanics is the spin -1/2, where you are aligned against the magnetic field. In other words, and on this axis, by the way, you're looking at energy. In the presence of an external magnetic field, there is a difference in energy between nuclei that are aligned with the magnetic field versus nuclei that are aligned against the magnetic field. And anytime there's a difference in energy, a quantized difference in energy, that's where we can do some spectroscopy to analyze that energy difference. Now, this energy difference, if you do the math, ends up being, let's see, on the order of 0.1 kilocalories per mole. And what that means is that a couple of things. If you want to calculate delta E equals Planck's constant times frequency, this frequency that that would allow a proton nucleus to transition from aligned with the magnetic field to aligned against the magnetic field is in the 300 to 900 megahertz area of the spectrum. That's radio frequency. So we've got the nucleus, we've got the magnetic. What is resonance? It's not used here in terms of like resonance in organic molecules. The process of resonance in this application is the transition from a lower spin state to a higher spin state. So nuclear magnetic resonance simply reflects the fact that in the presence of an external magnetic field, a proton or other spin 1/2 nucleus can be aligned with the field or against the field, and there's an energy difference between those two states. The energy difference is small, such that actually if you calculate an equilibrium constant and how many of the protons would be aligned with versus against, it's pretty close to 1 to 1. But that 0.001% difference or 2% difference is enough molecules to see and analyze. All right, so a couple of things you need to know about this frequency that causes the resonance, that is, causes the transition of a proton to go from with the external magnetic field versus against the external magnetic field. Questions actually so far? Yeah.
Could it be the 0.1, could that be either, or is it always on the positive spin state?
It's always lower in energy to be aligned with the magnetic field. Yeah. Okay, what else? All right, so a couple of conventions are going to help you. Yeah, sorry, was that a hand? No?
Yeah, so lower energy state would be like a ring then?
A lower energy state, we're talking about an individual proton, and a lower energy state is to be lined up with whatever your external magnetic field is. Where's the ring coming from? Okay. If you think of it, or if yeah, feel free to ask, and I'll show you some examples of how we can make these kinds of measurements. So the energy difference between spin states, and that is, again, a spin state is, imagine your little proton as a sphere that's spinning and has a magnetic field. It can be aligned with the external magnetic field or it can be aligned against the external magnetic field. We're not talking about protons actually moving their positions in organic molecules. We're just talking about whether the proton itself is lined up with the magnetic field versus not. So if you want to think of the proton as this tiny little charge ball spinning on an axis, you can, and being aligned with the field would be this way, and then it could rotate itself around to be aligned against the field. It's not actually how it works, but that's how you can visualize it. All right, the size of this energy difference depends on the strength of the external magnetic field. If the magnetic field is higher, the energy difference is higher, and therefore the frequency at which a proton absorbs is higher. The magnetic fields that are used on some of the instruments downstairs have a field strength of 14.1 Tesla. not vehicles, but that's actually a magnetic unit that was present, that was defined long before Mr. Musk started his company. 14.1 Tesla. That leads to an energy difference that is consistent with a frequency in the range of 600 megahertz for your average proton. So actually, by tradition, NMR instruments are described not in their field strength, but by the frequency, the average frequency that your average proton would absorb at given that field strength. So we have two 600 megahertz NMR instruments downstairs. We also have a 300 megahertz instrument. The 600 megahertz instrument has a stronger magnetic field. And if you go down there, there are actually lines on the floor, circles on the floor that indicate if you bring your phone or your credit cards within this region, they will be erased. And if you bring magnetic metal within this region, the force is going to get strong enough that it's going to be pulled away from you. So no metal, no magnetic metal anyway, near the NMR spectrometers. Yeah?
You have implants.
If you have...
You got surgery or something, you have...
is titanium, is titanium magnetic? If it is, then you're in trouble. If not, I don't think it is. So, yeah, but pacemaker, probably you get people to do the experiment for you. Yeah. Will it break the machine? It can cause damage, yes, because the force works on both things. So, a related instrument in this department several years ago, it had a strong magnetic field. It wasn't this kind of instrument, it was a mass spectrometer, but it was basically the same thing. To generate field strengths this high, you need basically superconducting electromagnets. So you have liquid helium that cools down a metal coil to really, really, really low temperature, and it's charged up and electrons circulate indefinitely and generate the magnetic field. But if you disrupt that, all of that energy can be discharged in the form of a rapid increase of temperature, which can cause a massive boiling off of the liquid helium and the liquid nitrogen used to cool it. Several years back when I was relatively new here, there was an instrument like this, as I said, and an undergraduate researcher was, I think, trying to impress their significant other by showing them this instrument, and for whatever reason happened to be carrying a wrench near the instrument, which was pulled out of their grasp, went up inside the instrument, knocked something out, led to a massive quenching of the instrument, and the instrument was really never the same again, and that was like a $2 million mistake. I don't think anybody held him personally liable, but there were some people who were upset. So anyway, got to be careful. Now, what we're going to see is that the frequency at which a proton absorbs radiation due to an external magnetic field is highly dependent on environment. So even though your average proton absorbs in the 600 megahertz region, your average proton is going to have frequencies that range from, 600 megahertz to maybe something like 600 600.6 I can't even figure out how to say this, but this number of hertz. So proton frequencies can vary over sort of a 9,000 or slightly plus or minus range of frequency values. And we want to plot these kinds of numbers on a graph, and the more digits you have, the harder it gets to pack in numbers on the x-axis. So instead of dealing with frequency, we're going to sort of normalize these frequency numbers to something called chemical shift. So for a given proton, chemical shift is defined as follows. You're not going to need to calculate chemical shift, but I want you to know where it comes from. It's given the Greek little letter delta, so that's several uses of the Greek little letter delta for you to keep track of. You take the frequency at which a proton absorbs, proton of interest, in hertz. Then you subtract the frequency of a reference proton, also in hertz. Your reference proton has 600 megahertz. And then you divide by the frequency of your reference proton, but not in megahertz. Not in regular hertz, in megahertz. So, for example, if this is our reference proton, and this is our proton of interest, you end up with basically 9,000 hertz divided by 600 megahertz, which converts to 15 times 10 to the minus 6, and we call that 10 to the minus 6 parts per million. I did not make this up, or ppm. So the units of frequency that we're going to use are going to be these dimensionless parts per million units, and it's just a way of converting a frequency of plus 9,000 hertz relative to the reference proton to something that's really easy to say, which is 15 parts per million. Okay? So that's history. It's probably not that relevant to you. You're certainly not going to be required to calculate chemical shifts, but I wanted you to know where the whole parts per million thing comes from. You can, if you want, just forget, you can take that particular nugget of knowledge and jettison it and reformat that particular part of your hard drive. All right. So let's deal with, go ahead.
All right, so I've heard that you need like certain amounts of fuel to combust, like you need however many parts per million. Can that also be interpreted as like for every million particles, 15 of them are this in order to have combustion, or is that something else?
Well, so parts per million or parts per billion or whatnot is often used in other places to describe concentration, like how much fuel needs to be in the air in order for a reaction to occur. I don't think it necessarily applies in that way here. It's really just what is the frequency of your proton relative to the reference frequency divided by the reference frequency, and it's basically what this does. I mean, think of it. If you didn't do it this way, then you've got to do 9,000 divided by 600 million. And so then you're going to be dealing with a number like this. 1, 2, 3, 4, 5, 6. Again, that doesn't solve your problem for digits, right? So the whole parts per million thing is just about converting this into a two-digit number that we can display on a graph. Yeah. Yes?
So in a molecule where these protons are bonded to atoms, does the bond impact what direction it can be in?
Does a bond impact the direction that a proton can orient itself in? No, not at all. But the environment of a proton will impact what frequency it resonates at, or what frequency causes a transition from with to against the external magnetic field. So we want to talk about that because the chemical shift of a proton you observe will tell you some key things about its environment. Now, just to show you an NMR spectrum, here is an NMR spectrum of this molecule E. On the x-axis, you're seeing chemical shift in parts per million. Again, notice that this prevents us from having to write 0.000008, 0.000007. Basically, if you're writing too many zeros, you should just change the units of your axis and make everybody's life a lot easier. All right. So, and then on the y-axis you have, it doesn't exactly mean this, but it's close enough for our purposes. You basically have absorbance, or how much, how high the signal is in terms of what you observe. So here you have frequency, and here you have on the y-axis extent of what is absorbed by your sample. I look at this spectrum and I see 3 different sets of what we will call peaks or signals, and these signals can tell me something about the molecule. First, notice that these 3 signals have different chemical shifts. That will tell me that they have different environments, and we will learn how to interpret the chemical shift in terms of what the likely environment of the proton might be. Second, notice that the shapes of the peaks are different. This single NMR signal is one single tall peak, which we will call a singlet. This set of peaks comes from a single kind of proton, but instead it has a characteristic pattern which we will call a triplet. And if you compare the sizes or the area under each of those peaks, the ratio is 1 to 2 to 1. That's significant, and we'll come back to that later. Another set of peaks over here at about 4 ppm has another characteristic pattern of 4 peaks, which we will call a quartet. If you take the area under each of those individual peaks, it would have a ratio of 1 to 3 to 3 to 1. That's significant too. For those of you playing along at home that like looking for patterns, you should start to see Pascal's triangle. There's reason for that.
So, when you're saying environment, do you mean what molecules it's bonded to?
Yeah, what atoms it's bonded to, what's nearby, yes. So we've talked about chemical shift. We've talked about the shape of the peaks. The other, and you get information from, for example, if I look at this peak that is a singlet, I can tell you now, based on what I know, that that proton is not adjacent to any other protons. We'll explain why that is. I can tell you, looking at this triplet, that the protons represented by this peak are adjacent to 2 other protons. I can tell you that this peak that's a quartet is a quartet because the protons represented by this peak are adjacent to 3 different protons. We'll explain why that is. Now, one other piece of information that you're going to get from this spectrum is the size or the area under each of these peaks. So the line here represents telling the computer to calculate the integrated area underneath the peaks from this point to this point after the peak. And that peak area is 23. 23 what? 23 arbitrary peak units. What do you want from me? It's not anything that you need to worry about, only that it be consistent from peak to peak, all right? So this one has 23 arbitrary peak units, this one has 29, this one has 30. The area under the peak will be, and this is really cool, proportional directly to the number of protons represented by that peak. So looking at the areas under each peak, there's a ratio of 2 to 3 to 3. Now, I don't know at this point whether that means that there are 2 protons here, 3 protons represented by this peak, 3 protons represented by this peak, or whether it could be 4 to 6 to 6, or 8 to, whatever. I don't know any of that yet. I just know the ratio between peaks. And that can tell me, that can help me assign which peaks are generated by which protons in my molecule. Finally, if there are going to be multiple protons per peak, you have to come to the conclusion that identical protons, protons that are identical by symmetry, have the same NMR signal. So it's possible to have two protons that are identical and show up as the same peak in the NMR experiment. And in fact, that's exactly what's going on here. I have two identical protons that are showing up as one peak. This represents three identical protons. This represents another three identical protons. Now, what structure do you know of in an organic molecule where you can have two identical protons? What is a common structure? Oh, come on, you've drawn this like a gazillion times. What is a common structural arrangement that gives you two identical protons? Nobody? An alkyne? Well, okay, fine. Yes, you are right. Good? Yes, that's good. But in a larger organic molecule, a CH2 group would be two identical protons, right? So this is probably a CH2. Now, what common structure do you know of that has three identical protons? A methyl group, right? So this is probably a CH3, and this is probably another CH3. We're seeing the pieces put together. We have accounted for the carbon-oxygen double bond. We know there's a CH2, a CH3, and a CH3. We've almost solved this thing. So when we come back next time, we'll deal with all of these things in greater detail.